So as I said, I am a university professor. I'm a professor at NYU. And one thing that professors love to do is we love to give quizzes. And so I have a pop quiz for the audience here. No cheating if you saw this same quiz yesterday. But there's an attack vector that's used by some of the best hackers in the world. It's completely invisible and isn't protected by different network defenses, like your firewalls, your IDSs, things like that. It's something that impacts and can impact basically every device, just about every device on the planet. So almost everything can be hit by this attack vector. It gives you usually things like root access on the devices you get on, and it's already been used to great effect by nation-state actors around the world. Which are the best hackers in the world, use this over and over and over again to do some of the most damaging attacks that we read about in the news, and we're like, oh my gosh, that's terrible. All right, and then I'll just go ahead and kind of give you the answer here. There's many victims to this type of attack. All of these companies here, these are, I think, companies like Google and Microsoft and others that you would think of as having some of the best security teams and some of the best security postures. Yet they've all been hit by this. And this attack, as you would know if you understand what session you're in, is actually attacks that deal with software updates and attacks through software updaters. So there's this massive risk and vulnerability here. And so there's this question of, well, it's easy, right? We just use crypto. Just like, hey, I have a bike I want to lock up here, and I just put my lock on the bike. And then everything's okay. Like, no one could possibly steal this bicycle, where, of course, you just, pick it up and walk off with it, or lift this latch over the yellow part and then ride off with it, or whatever you like to do. What we need is a solution, and sometimes a simple solution doesn't always give you the properties you want. And in this case, one simple solution that is the reason why some of those companies ended up on that first slide was basically what they said is, we're going to just use TLS protection. You're going to have X509 certificate. You go to the site. You're talking to the server. So if you're talking to the server, what can possibly go wrong? Well, what can possibly go wrong if you're talking to this server here that's responsible is that someone breaks into the server. And then when they break into the server, you're talking to the server, but you don't, the server could be sending you any kind of malicious software or doing anything like that. And this is something like a web server that has, a web server on it, right? So it has complicated software. It's running a full stack. It's, and TLS itself has had a lot of historical issues and problems over time. So this is not, I think, the only line of defense you want to have in a system like this. The other solution that people have taken historically is they use something like a key, often something like maybe GPG or something like that, that might live on a server. And maybe what happens is you have all your developers for some big Linux distro, and if you're in the trusted group, then your key is trusted. And so then what happens as a result is if you're one of these developers, you're trusted in most cases to sign anything that it comes from that distribution. So you might be the developer whose main thing is you do the translation of some of the documentation into Bulgarian. But you could still sign the Linux kernel package because your key is in the key ring and it's trusted. And that's bad, because then if any of these developers are hacked, potentially all the users can be compromised. And so one way that some environments try to protect against this is they have this server, like maybe a build server or something like that, that has a key on it. And hey, the build server will sign things and do stuff. But then you break into the build server, as we've seen happen time and time again, and people are hacked. Okay. So now we've kind of talked about how, all of those, like the models that people have commonly used that has ended up with them being on that kind of slide of shame I had earlier on. So now let's look at, is it even possible to do something better than these simple designs where if something goes wrong, you're in a world of hurt? And it is. So we started with the goal of doing this back in 2009, 2010. I had done some work on vulnerabilities and problems inside of Linux package managers, and had written some papers and worked with the major Linux package managers to fix those issues, like the design flaws in with what they were signing and how they were, verifying and looking at metadata. And the folks at the Tor project came and said, hey, we realized we have some big problems in Tor. Can you, help us to design a better updater? They came and spent a couple of days with me when I was at the University of Washington, and came back later with a suggested design. And we looked at it, and myself and an undergraduate student who was working with me looked at it, and we found a bunch of flaws in what they had done. And the realization at that point was that this is actually a very hard problem. So if experts who are like world-class security researchers, there's nuances in this problem they're not seeing, then maybe the right solution isn't to go around and tell everybody you need to fix these 37 things. The right solution is to build like a common framework that just sort of does it right. Just like we don't go around and tell everybody to do all the right sorts of things for like TLS, et cetera. You use libraries that people have written that basically handle your communications and give you confidentiality and integrity and authenticate who you're talking to and so on. So what TUF does, and what the goal is that you have a situation like you have before, where you have some server that maybe gets hacked, but your users are not at any real risk from this. So what I'm going to talk about briefly is how TUF does this, how TUF makes this happen. One of the other design goals inside of TUF, besides this idea of being able to be resistant to compromise, like don't just assume you're going to be operationally perfect, one of the other things TUF does is it tries to support use cases that you have, because the real world looks like this in many cases. And so TUF is not something where it says, thou shalt have fingerprint readers on every commit, and you have to take a DNA test to do this and do that. It's meant to be able to be plugged into existing systems easily, and then over time you can tweak things and improve your security. So it doesn't force you into certain configurations. All right, so there's 4 main things that I'm going to talk about with respect to TUF's design to try to give you a sense of how it provides the properties it does. The first one is called responsibility separation. So the idea here is that what you do is you have different roles that different parties in the system will do and will provide. So for instance, your repository is going to be responsible for doing things like saying, has there been an update that's been updated? But your developers are the ones that say, this is a valid update. So what this does is this makes it so that if someone breaks in the repository, they might be able to lie to you and say, there isn't a new update from this developer right now, but they aren't able to tell you this is a valid version of this specific package. Okay? And we'll look at some examples of this. One other like kind of sub way of doing this that's helpful is a developer for a project can go and actually sub-delegate to other developers some subset of what they're able to do. So for instance, if you have a project, a software project that you're working on, and you have someone come and is a new contributor, and let's say that they're building a version of the project for an environment that you're not able to test well on. Like they're a Windows ME enthusiast, and they're going to build a Windows ME of whatever your software is, Windows ME version. You can delegate to them and say they can build the Windows ME version without just, for instance, needing to do something crazy like give them your key, which would be insane, or giving them trust for everything in the system. Okay, and I just talked through this example, so I'll skip that. One of the other things TUF does as a design principle is it tries to make it so that the overall risk you have in the system is as low as possible. So you can think roughly about the expected damage to happen in a system as being the probability of an event times the impact if that event does occur. Okay? So there are certain things where you're able to go and make the probability needs to be very high. So the probability of somebody breaking into your server, like your repository, is actually a very high probability event. So you want to make the impact of that very low. So for instance, as I talked with my example before, the repository might only be trusted to do things like say, has there been an update in the last, like in the last day? But it's not trusted to sign things. And then situations where you have something like a root of trust that needs to be protected, then TUF is designed so that it's operationally convenient. It's not inconvenient for you to do things like have YubiKeys that might get stored in safety deposit boxes or or locked desk drawers across multiple different sites that collectively go and sign and provide things for that role. And so the sort of thing that would have to happen, like the probability of someone going in and getting those means that they have to do some Mission Impossible style heist where they have to break into multiple sites at the same time, steal things out of your offices, out of locked drawers, and then come together to sign some metadata, which is pretty hard to do, to put it mildly. Right, so if you have a high impact role, then highly secure, we make it so it's operationally, it's not operationally burdensome to have highly secure keys. And online keys, things that you have to keep online, we make the impact very low in the system. Another thing that we do is we have this notion of multi-signature trust. So I alluded to this before in my example, but you don't have to have a single party that is the one trusted true source of truth. You can have a situation where there's two parties like A and B that both are required to sign a document or sign a package, and you can set up these thresholds however you want to set it in your system. And then if A gets compromised in a situation here, there's no risk to clients. There's no damage if A is compromised. You have to have both A and B get compromised. And after A is compromised, well, what do? You handle the last part here, which is dealing with revocation in the system. So when we first did the design of TUF, remember the goal of TUF was to protect in situations where your server's compromised. That was like goal number one. How do we do this? So revocation is very much built into and was a primary concern when we were designing TUF. If anyone here has ever dealt with revocation in revoking in the X509 CA world or revocations inside of GPG, you know that is not the case for those systems. Revocation is really messy and clunky and doesn't work well and it just doesn't behave in a way that's sane and logical. And because this was a focus of our system, revocation is actually very simple and very seamless inside of TUF and isn't some weird out-of-band channel that happens naturally. We also have multiple ways to do revocation where you can both explicitly revoke something, for instance, by taking your Windows ME intern who used to work with you and just removing them from the delegation in your metadata that you generate. That explicit action revokes their trust. Or you also have metadata in the system that expires at different times. So you can implicitly say things like, for instance, if you haven't seen an update for some period of time, you should consider that you're being blocked, as actually does happen in practice by several countries that want to keep their users on older versions of software so that they can presumably exploit dissidents' devices. Okay, in TUF has four main roles. TUF has the root role, which serves as the root of trust for the system. This is it was the example of the keys you have spread apart in safety deposit boxes that only get brought out when something goes wrong, or only get brought out every maybe 3 to 6 months to make sure that a large number of them haven't been lost or ceased to operate, because, I don't know, somebody spilled their coffee in the desk or something like that. There's something called a targets or projects role, depending on when and how TUF is used. The names for this differ. But this is basically the developer that's going to go and say, this is a valid version of this thing that I'm creating. Okay? This says this is a valid package. And this is, in practice, it's basically always done by somebody either having something like a YubiKey or by going and on their device having their GPG or whatever key that they're using. So think of this as the same sort of, you can in fact use the same key you might use for your Git signing or for other operations like that that you do. It just now is plugged in here. The snapshot role, I'm going to skip for just a moment and explain it in a sec. The timestamp role lives on the repository and says when the last update has happened in the system. And what the snapshot role does is it's used to handle a very special or a very useful attack case that otherwise would go unhandled. And this attack case deals with situations where, so for instance, if you go to like a Linux distribution and you say, give me package X, and what you get back is you get that package back and you check to see if it's signed, you have a big problem in there. Because the signatures that are done are often with keys that are quite old, and older keys still tend to be trusted. So what you can do as an attacker is you can do something like provide someone with an 8-year-old version of SendMail in some cases, or some other thing like that, and they don't have a way to know that this isn't current and valid. So what the snapshot role does is it effectively manages letting clients that come to get updates know what the latest version of all the software on the system is according to the targets, okay? So it's not allowed to sign this, but it's allowed to tell you that the latest version of the metadata about the packages are these. And so this prevents a huge class of attacks that are very hard to prevent in other ways. Okay, so TUF is not a hypothetical thing. As you might realize, of course, we're a CNCF project and incubating, and we're I think 1 vote away from graduation. So if you know a TOC member that hasn't voted for us yet, then tap them on the shoulder in the hallway. I saw Joe Beta out there as I was walking. TUF, a lot of the early things that happened with TUF is we worked with the Python community very early, and it's been standardized in that community through a couple of PEPs. They're doing integration now. They actually just redid they've received money for integration and have picked people that are doing this and are in the process and so on. But they redid their PyPI, and so it's taken them a little longer. It's quite used inside the cloud. The reference implementation of TUF, which comes along with the specification, is used by a few different organizations, most notably Datadog. And Notary, which is another CNCF project, which is created and maintained by a bunch of different folks, but primarily by folks at Docker, like Justin Cormack, is widely used by a lot of different companies. Google, Amazon, and Flynn have all created their own implementations of TUF that they've open sourced. And in addition to that, there's an automotive variant of TUF called Uptane. Uptane is widely used in automobiles because the automotive industry is extraordinarily secretive. I have to be a little careful about what I say in this public forum, but there are multiple OEMs in the United States, multiple OEMs in Japan, and multiple OEMs in Europe that have adopted Uptane. And some of the projections that we and others have done show that about 1/3 of new cars on US roads in 3 years will be using Uptane as a way to deliver over-the-air updates. So it's had a lot of impact in that space as well. Uptane itself is also standardized both by IEEE ISTO and under the Linux Foundation's JDF. So we're currently being hosted under that. And now I want to just very briefly talk about what happens when something goes wrong in TUF. And this diagram, I think, is a pretty easy way to see this. So if someone breaks into your repository, then they probably steal these 2 keys. It slightly depends on your setup. Some people do timestamp on mirrors and stuff like that, but they probably steal these keys. And the things you're really probably most concerned about is somebody able to do bad things? And after you find that somebody has done something on your system, can you securely recover, or are all your users basically in trouble? As would be the case if you just had like a GPG key, where if someone steals the GPG key and then, let's say that a Linux distro figures that out and then tries to send an update to say, this is the new GPG key, you should trust us instead, you don't have any way to know whether you're talking to the attacker or the distro. Okay, so in the case of someone breaking into a repository, breaking into a developer only, then there's no ability to install malicious updates and they can't securely recover. If they've compromised a developer key and they've either tricked or broken into the repository, then they can do this, but only for whatever project the developer has access to. So, it's not like, if you steal one Debian developer's key, then all Debian packages are suspect. It's just whatever that developer is able to do, and you have a secure way to recover. If they try to do that Mission Impossible Ocean 11 thing and break into all those desk drawers for your root keys, then if they don't steal a threshold of them, then you can rotate out securely and there's not a problem. But if they do manage to get the Acrobat stuffed into the little tray thing and all the other stuff like that, and do a threshold, then yes, you do actually have a problem in the system. Okay, so with that all being said, now I'm going to hand it over to Santiago, who's going to talk to you about how we protect about a whole bunch of things that TUF doesn't protect against. So Santiago?
So can you guys hear me? Okay, so now we know that what you can do in the last mile. We know how you can provide a package from the repository all the way to the user in a safe way, and a way that can also recover from compromise in different levels. But that's not the whole story. You may be wondering how that package made it there. And in this case, I want us to look at a very cartoonish, very simplified version of a software supply chain. You probably have code in a version control system. You probably put that code in a build farm that builds the source code. Then it pushes it out into a packaging infrastructure that probably ends up hosting that package so the users can get their updates or their new packages. You may also even have a CI/CD system that's constantly running tests on the packages that you are updating and you're programming with. So you wouldn't be surprised, and this is a security talk, that there can be compromises that can, in the same way that the repository compromise can happen in other stages of the software supply chain. You have things like tampering with Git metadata, or people that break into the version control system and change source code as it is checked in, or after it's checked in if it's not signed. This is not a theoretical attack. This has actually happened many times. There was a very prominent attack on the Juniper firewall in which somebody broke into the Juniper firewall source code and changed the pseudo-random seed in such a way that the whole IPsec stack was decryptable. People even point fingers to nation-state agencies. The whole story is actually a little bit disputed, and there's many questions about what actually happened. But again, this is not an isolated incident. There's been many people that have been targeted on the source code level. And in the same way that can happen to a version control system, it can happen to a build farm. There's a big Turing Award lecture about backdooring compilers, but there's also a very practical attack that happened, or a very actual situation that took place was Xcode Ghost. Is anyone familiar with Xcode Ghost? Well, Xcode Ghost was a backdooring version of the Xcode SDK, was published in a couple of servers. People downloaded it, and any iOS app that was built using this version of Xcode Ghost had a backdoor in it. This iOS apps eventually made it to the App Store and eventually made it to users. And if we're thinking about blast radius, just think about how much people you can attack by using these attack vectors. The same thing happened to the Fedora infrastructure, FreeBSD. Again, this is not an isolated incident. I am not trying to shame anybody, but this is the reality of the situation. We already spoke about packaging infrastructure. I'm going to skip fast through this, but I want to make a quick PSA. If you are a user of Monero or know anybody that uses Monero and have downloaded the wallet in the last 20 days, there was a compromise on Monero software as of the 24th of October, and many people have downloaded it and have their funds stolen, or will have their funds stolen as soon as they open the app. This is real and recent. Now, the same thing can happen even at levels of compliance. There was instances of Windows updates, buggy Windows updates, making it to the users because the QA team or the release manager wasn't able to sign off or didn't sign off, or did sign off, and people weren't able to enforce this sign off appropriately. And this means that users have to pay the cost of flaky ways of enforcing compliance. Now, I am sure that probably many of you saw this like stylized software supply chain, this very simplistic model, and thought, well, we actually do things more complicated than this, so why are you telling me this in such a cartoonish, simplified, idealistic way? But even in this 4-stage, like very even primitive software supply chain, there's many avenues of compromise. And I've wagered that in 6 of the 8, they result in full compromise of all of the user base of your software product. So how can we address this? Now, many of you may know there's many good solutions. For example, if you're using Git, you should be signing your commits. If you want to bump it up, you probably want to use Git push certificates, which is a way to sign not only the Git commit, but your references as you push them out to a server. If you're working on a build farm or you have a build infrastructure, you probably want to start looking at projects such as reproducible builds and start thinking about using HSMs and DPMs to ensure the integrity of your build infrastructure as it's building your packages. Finally, we've spoken about TUF, but even if you use TLS and GPG, that may even be a bump in security on what's sometimes the status quo in many of the projects out there. Now, even with point solutions, you may not be fixing the whole problem. Now, I took the liberty of deleting some of the devils on the picture that had 8 devils, and now we are down to roughly 5. Am I counting right? 6 devils. This is because there's a question of gaps between steps. Even if you have a point solution in place, how are you able to know that this point solution was A, followed, and B, that the result of the security measures on this point solution were actually considered in later steps down the line? So we have point solutions, and we are not trying to remove these point solutions. We're trying to make it so that you can comply and enforce that these point solutions are in place. So we came up with in-toto. In-toto is a very simple way to define what point solutions or what needs to happen in each individual step in the software supply chain. B, who can take or can partake in the actions in each individual step in the software supply chain. And C, to ensure that there's integrity as these artifacts or source code or images or packages flow down the chain into further steps down the chain. So we do this with 2 pieces of information. The first one is called an in-toto layout. If you are familiar with Jenkins files or make files, you'll probably find this similar. It is not a declarative or a executable piece of information, but it does describe what we were talking about just here. It says, well, these are the steps that need to happen. It defines the operations in the software supply chain. It also defines the actors that need to or can partake in the operations in the software supply chain. You have Dave, which is running the Travis CI infrastructure, probably has a private key and can sign for these operations. So you are sure that Dave is the one that's actually running everything on the Travis CI. You also have a mechanism to register or comment on what are the artifacts that are created and consumed throughout the chain. When I say artifacts, I mean, for example, the version control system, it is source code. For the build farm, for Carl's build farm, you may be producing binaries. For Aaron, you may be consuming binaries and producing a Debian package or a Docker image or anything that's publishable and consumed as a sort of package. And finally, we want to ensure this integrity element of how these artifacts flow through the chain. We want to make sure that the source code that was created and reported by Bob, the version control person, was the one that was passed down to the build farm and not any other version of this. And finally, just to make sure that we have an integrity and an authoritative source of truth, we want to have a signature over this piece of information so we know that either the project owner or project manager or the I don't know, BDFL of an open source project is the one that's telling us what needs to happen. Now that we know what needs to happen, we also need evidence of what happened so we can compare it and make sure that this is actually what happened. So we have this other piece of information. We call this in-toto links. Think of this as attestations that have integrity checks of all of what was taken in and all of what is pushed out or created. And it also has a signature by this specific functionary. It's a cryptographic signature that can be used to ensure that the person who performed this operation is indeed the person that should be performing this operation. Finally, when we have all of this information collected, you can essentially run a verification routine that takes this layout and in this policy language and compares it against the evidence in the link metadata and makes sure that everything is followed according to the letter. There is many users of in-toto already out there. There is Datadog, which is through Datadog, it's protecting. Many of you probably are using services on that box, and you are thereby protected by in-toto. There's other users that are using in-toto in different ways. The nature of in-toto that lets you represent different supply chains in a very flexible and rich way makes it so that it's easy to implement in many of the different ecosystems. I am actually, because I've given demos of other things, today I will try to make one of the quickest demos in the world, but Debian is working very hard in the reproducible builds project. And something really cool that you can do with in-toto is there's rebuilder organizations. One of them, for example, is Microsoft. Another one is NYU. There's University of Bergen. They're basically monitoring what Debian is building and pushing out in their official repositories, and then they are pulling out this information. Then they are rebuilding these packages, and then they are publishing in total link metadata, this evidence that I was talking about. Then there's a layout that I'll show you in a second that says, well, all of the people who rebuilt this, of these different organizations that we trust, need to agree on the result of each individual package that you're downloading. So I'm going to go ahead and do this. We are pretty much on the line, so I'll try to be quick. This is the wrong demo. So probably, yep, here we are. So I'm going to spin up a little cluster. Is this text readable? It's probably better. We have a malicious mirror. We have two rebuilders that are rebuilding our demo package. Then we have a client. And then we have two malicious mirror, one malicious mirror, one client, one good mirror, and two rebuilders that are rebuilding our demo package. So I'm going to quickly jump here, and if I didn't screw up, I should get a shell. Did I get a shell? Oh, yes. OK. Do I have bash just so we? OK, cool. So we're here. All of what I have to do is make this little edit. And right now I have HTTP, mirror OK, Debian. I am going to change this to in-toto. Then I'm going to apt-get update and apt-get install demo package. So what this is going to do, it's going to, there's a bunch of things that went on here, but is this blue? I think it's blue. Basically, it downloaded the Debian metadata. Then it downloaded a bunch of attestations that said all of the package that you downloaded was rebuilt by enough people so that you can trust that it was reproducible build and by the people that you trust. So this is very uneventful, so let's try to do something different. I'm going to switch this mirror for a bad mirror. And then we're going to do the same. I'm going to remove this guy just so we can install it again. And then we're going to install it again. The malicious mirror, of course, was being malicious. It actually replaced one of the packages with a malicious version of it. But even though it was signed by the right people on the Debian side, on the keyring that we injected, the rebuilders didn't agree with that result. So we were told that there was not a threshold of people that agreed on the reproducibility of this package, and thus you are not going to install it. There's, of course, questions that we can address about the usability of this tool. I think it's a little bit rough on the edges right now, but you can do things like this with such an expressive mechanism. So just to close up, this is not the work of just me and Justin. There's many people involved and working very hard. And it should be, it would be great if you guys got involved and reached out to us when like use cases and different supply chains and ways to make in-toto and TUF protect your whole software supply chain.
All right. So thank you. I think we possibly have time for a question, but we're kind of semi-over. Yes?
What's next? What are you working on right now?
Yes, so that's a great question. Specifically on this Debian and reproducible builds. Well,
In Toto in general, but
yeah, yes. So there's work on making, first of all, full software, hardware secured software supply chain security using in Toto in such a way that you can use taint analysis information and carry it through these attestations. And you can have a hardware accelerated in Toto secured piece of hardware. I think that's pretty cool. That's actually some work that we're trying to do with the SPDX and the Zephyr project, which is a real-time operating system that's being used in like many different environments. There's also work on the Debian side on making not only this metadata available by different rebuilders, but this rebuilders gossiping a transparency log in such a way that you can have a high availability case for all of the in-toto metadata. And finally, we're trying to find sketchy cases of these software supply chain compromises, like the Monero that I just spoke about. We've been finding that there's many deep supply chain dependencies that can be used to cause and wreak havoc on users.
Yeah, and we're also looking at how to better secure like the initial root of trust that you get from whatever parties you do, and ways to layer this into things like community repositories like pip and Ruby gems without them actually having to do any work. So just a way to bootstrap trust in the system securely, or as secure as we can do. Any other questions we can answer for people? All right, well, we'll be here offline, happy to chat with anybody. So thank you all for coming. Thank you.